Hello, this is the second session of our course in differential geometry. So today we will be discussing the notions of tangent spaces to manifolds, and derivatives of smooth maps between manifolds. Also, towards the end of this course, I will raise a question. You're welcome to share your answer if you like. Okay, so loosely speaking, today we want to consider smooth maps like f between two manifolds m and n, and we want to define derivative of f at a point x, where x is a point in M. This would be quite fundamental in our course. Okay, let's start. Let's go back to fundamentals, like basics, right? Let's go back to calculus. So in calculus, we used to study maps like f, smooth maps between Euclidean spaces, right? A map like f from Rk to Rl, where k and l are two positive integers, right? Let's pick a point x in Rk, and let's say it goes to f of x in Rl. So schematically, let's say this denotes Rk, the domain of our map, and this denotes Rl, the codomain of our map, right? And this is x, and this is f of x, right? Okay, so what is derivative of f at a point x? So by definition, this is a linear map from Rk to Rl. So the most probably important thing is that this is a linear map. So let's write that in red. So how is it defined? Okay, so I should say what is d of f at x acting on a vector v. Let's say v is a vector in Rk, right? Let's say this red vector is v in Rk. So this is defined using a limit, as one would define derivative, limit of f of x plus tv minus f of x over t, where t goes to 0, right? This limit, if it exists, this is the definition of derivative. So what does this mean? What is the geometric intuition of this? Let's say this other vector in codomain is the image of derivative acting on v, right? Okay, let's kind of move Rk so that it would be based at a point x. Like now the origin is x, so it's just moved Rk, so it's based at the point x. Let's also move the vector v so it starts from the point x. So what is the point, where is the point x plus v? So this is this black dot where the terminal point of v is kind of pointing towards the. Let's do the same thing on the target space. Let's move Rl so it's based on f of x, and also let's move the vector df x of v to f of x. So loosely speaking, f of x plus v, we can approximate that using the derivative. So an approximation for f of x plus v is f of x plus derivative of f at x acting on v. So derivative is like the linear approximation. In fact, it's the best linear approximation, right? Just like we had for one-dimensional functions. The fact that it's linear is essential. So let's just recall, what does it mean for a map to be linear, a map between vector spaces. So if you look at the fx, if it acts on v1 plus v2 for two vectors v1, v2, it would be equal to derivative acting on v1 plus derivative acting on the vector v2. That was the first property. Second, derivative of f at x acting on cv, where c is a real number and v is a vector in Rk, is equal to c times derivative of f of x at acting on v, right? Okay, great. So derivative is linear in this sense, right? Okay, now, so we want to see what does it mean to define this notion for manifolds rather than just maps between vector spaces. So before doing that, or for doing that, we are going to use a few essential properties. The first important property of derivative, just on Euclidean spaces, is that it satisfies the chain rule. What does that mean? Let's say we have three Euclidean spaces, Rk, Rl, Rp. And let's say we have two smooth maps, F and G, between them. We can define a new map from Rk to Rp defined by GOF using the composition, right? Now we want to see what is derivative of GOF at a point x. Okay, look at derivative of f at the point x. It would be a map from Rk to Rl. Look at derivative of g at f of x. It would be a map from Rl to Rp. This linear map agrees with derivative of GOF at the point x. This is what we call as chain rule. The second property is that if we think about the identity map on Rn, the derivative of this map at any point is equal to itself. Right, it's a linear map. In fact, more generally, for any linear map on any Rk to Rl, the derivative of the linear map at any point, so let's say this is linear, L is linear, derivative of L at any point x equals L itself. So linear map in some sense is the best approximation of the best linear approximation of itself, right? Okay. Now let's get back to our main motivation. Let's say we have a smooth map between two smooth manifolds. Derivative of f, we like it to be linear. We want derivative to be a linear map, approximating the map f close to a point x. For the map to be linear, the domain and target should be vector spaces. Domain and target also should be linear. M and N are manifolds. They're not linear. So how can we define domain and codomain so they would be vector spaces where M and N are potentially curved? They are manifolds. They are not vector spaces. The vector space we are going to use here, these linear spaces, are linear approximations of our manifolds M and N close to the point x and f of x. In fact, this is what we call tangent space of our manifold at point x or at the point f of x. So this is the first thing we should be doing. We should be defining tangent space. Okay, let's kind of think about this more intuitively and pictorially first. Let's say we have a manifold, we have some manifold M in Rk. Let's say we pick a point x on M. The tangent space to M at the point x is this flat affine space tangent to M as a subset of Rk, just like the way we had tangent to a line. That transferred to the origin of Rk. That's what we call tangent space to M at a point x. Okay, that's just kind of, for example, for this torus, it would be just a plane inside R3 tangent to torus at the point x. But here we are assuming the manifold is embedded. It's sitting inside some Euclidean space. What does that mean? Any smooth manifold M can be embedded, or it can be understood as a smooth subspace, submanifold of a Euclidean space Rk for some large k. What does it really mean? Look at this circle in R2. In some sense, it's sitting inside R2 in a smooth way. Same topological space can be embedded inside R2 in a non-smooth way. You see these broken points? This subspace or this subset is not a smooth manifold. It has broken points, right? Okay, so what does it mean? What is the definition of smooth embedding or a manifold sitting inside Rk smoothly? Okay, so let's again kind of take a point x. I would say the manifold M has smooth embedding in Rk if at any point x on M there is a small open neighborhood W inside Rk, which includes x, a map phi from Rm, where the manifold M is m-dimensional, to Rk, which is smooth. Domain is either Rm or some open subset in Rm. That's not very important. The map should be smooth, injective, and derivative of this map at each point should be injective, right? As a map between Euclidean spaces, we understand the derivative in the calculus sense. So this should be also injective. So let's say this is Rm, where our manifold is m-dimensional. There should be some open set U where the map phi takes you to W, such that, let's say, the image of U is exactly equal to M intersection W. So it takes this, well, in our picture, there's an open interval U, schematically. The map phi should exactly take that to a neighborhood of X inside M intersecting W. If that's the case, we say we have a kind of smooth embedding of M inside Rk. So let's suppose, for the kind of sake of defining tangent spaces, let's first assume our manifold is embedded inside some Euclidean space Rk smoothly. Let's pick a point X. So again, pictorially, let's say this is M sitting inside Rk, there is a point X, etc. Now I want to define tangent space of M at the point X. Because the manifold is smooth, there is an open subset of X inside M, not inside Rk, but inside M, and a map phi which takes you to an open subset of Rm, right? Let's say to V. This just comes from the definition of smooth manifold. Let's say phi of X equals U for some point U. Now, on these open neighborhoods, phi is 1 to 1, so we can consider phi inverse. Phi inverse would be something from V to U, right? So U is inside M, M is inside Rk, so phi inverse is defined on an open subset of Rk, and the target is a subset of Rk. It's from an open subset of Rm to a subset of Rk. This is a map between Euclidean spaces. We know what is the definition of derivative of map between Euclidean spaces. So look at the derivative of phi inverse at point U. It's a map from Rm to Rk, right? It's a linear map. Linear, great. We can look at the image of this map. So d phi inverse of U acting on the whole Rm would be a linear subspace of Rk. Look at the image of this map. It's a subset, vector subspace of Rk, right? This is what we call the tangent space of M at X. So look at this pictorially, this blue plane tangent to M at the point X. If you translate that to the origin, it would be exactly this image, this d phi inverse of U acting on Rm. So d phi inverse of U acting on Rm, looking at the image of that, is a vector subspace of Rk. It's exactly the kind of flat space tangent to M translated to the origin, right? That's what we call tangent map. It's a linear space. There is something a bit negative about this definition. One might say, I want to think about manifolds in an abstract way. I don't want to use specific embeddings inside Euclidean spaces. I want to define the tangent space independent of the embedding. That's a good question. There is a kind of different question. One can say, well, maybe I wouldn't take phi. Maybe I would take different coordinate map around X. So it's essential to understand the notion of tangent space is well defined. It doesn't depend on the open set U and the map phi, the parameterization, or the coordinate map we picked. If you take another open set U tilde and another map phi tilde, a coordinate chart around X, the tangent spaces these two define are the same. The image of the inverses of these two things defined on Rm would give you the same vector space in Rk. Okay, so in this sense, this notion is well defined. But still, it's nice to try to come up with a definition of tangent space in a more kind of invariant way without using specific embedding of map inside Euclidean spaces. Okay, let's get back to our main question. We have a map F from M to N. What is derivative? Before defining it, now we can say what is the domain and codomain. The derivative of F at X is a linear map from tangent space of M at X to tangent space of N at F of X. Now these two tangent spaces are vector spaces. They're linear. It makes sense for d of F at X to be linear. So if M is embedded inside Rk, N is embedded inside Rl, the tangent space of M at X would be a subspace of Rk, right? And tangent space of N at f of X would be subspace of Rl. What is the definition of derivative? Well, take a vector v inside tangent space of M at X. Derivative of f at X acting on v, like in a similar fashion, is defined as a limit. Limit of f of X plus tv minus f of X over t when t goes to 0. There are two things to note here. X plus tv is defined. It makes sense because this sum is made inside Rk. And f of X plus tv minus f of X also makes sense. This subtraction is happening inside Rl. Dividing by t also makes sense. We are dividing a vector in Rl by t. So that also makes sense. You know, everything is happening inside a linear space. Okay, so now we have the notion of tangent space for embedded manifolds in Euclidean spaces. We have the notion of derivative, right? There is a different way to define derivative. One person might say, I don't want to use the fact that M is embedded inside some Rk, N is embedded inside some Rl. I want to define derivative of f in a more kind of invariant way, independent of one fixed embedding. Okay, pick a point x in M and pick a point f of x in N. So, you know, let's say schematically this torus is our domain, this sphere is our target, there's a point x going to f of x. Because M is a manifold, there's an open subset U and a map phi taking a neighborhood of xu to some open subset in some Rm, assuming M is m-dimensional. F of x would have a neighborhood V and a map psi, taking that to our N, let's say. The manifold is n-dimensional. Now, using this composition, psi of f of phi inverse, we can go from a subset of Rm to a subset of Rn. We want these maps, we want to define df such that this diagram would satisfy the chain rule, in the sense that d of psi of f of phi inverse at any point, say u, let's say u is a point where using phi inverse it goes to phi, goes to x, we want this to be equal to what chain rule says, right? We want it to be equal to d of psi at f of x or d of f at x, d of phi at phi inverse at u. So the second way to define derivative is that derivative of f at x is the function, is the map, is the linear function that satisfies this formula. So this is called definition using the universal property. You're defining f using that, the fact that you want it to satisfy this rule. You might say we are still using the fact that M is embedded in some Rk, N is embedded inside some Rl. We are using some fixed U and phi, V and psi. That's not true. Here we are not fixing any embedding in Rk or any specific open set U or phi. We are saying for any embedding of M in any Rk, for any embedding of N in any Rl, for any open set U and map phi, for any open set M via map psi, for any such choices, d of f of x should satisfy this property, not for any fixed one. Nothing is fixed. For any embedding and any coordinate map, d of f must satisfy this equation. This would define d of f. That's a kind of good thing to practice to see why this uniquely determines what the derivative should be. Okay, a few remarks. Let's say we have a smooth manifold M. Let's say we pick a point x. Let's say we pick an open neighborhood U around x. Since it's smooth, there is a coordinate map to some Rm, to some open set inside Rm. D of phi inverse at the point U where U takes, phi of x equals U. D of phi inverse U. We can now apply this linear function to the basis of Rm, E1 up to Em. These would kind of give you tangent vectors to the manifold M at the point x. We usually denote this with partial x1 to partial xm. These are m, you should think about them as m tangent vectors to m at the point x. Actually, we usually write, it's better to write indices above x, x1 to xm. So the map phi inverse take these coordinates inside Rm to some local coordinates inside, the manifold M, like these curly things. And derivative of map takes the basis E1 to Em to these tangent vectors. In fact, the tangent space of M at the point X is generated by these tangent vectors, partial x1 up to partial xm, where the manifold is m-dimensional. The second remark, we mentioned if x and y are two smooth manifolds, their product has a smooth structure. If you pick any point x and y, where x is in x and y is in y, the tangent space at x and y is equal to tangent space of x at x and tangent space of y at y. Note that the first product is product of smooth manifolds. The second product is product of vector spaces. So the left-hand side can be essentially canonically identified with the right-hand side. The third essential property is that there's a different way to think about tangent space, and that's using smooth curves inside the manifold. Again, let's say we have a smooth manifold M, a point X. We can think about curves like gamma, smooth maps from an interval, say from -1 to 1, smooth maps to M. So their image is a smooth curve inside the manifold M. Let's say gamma sends point 0 to X. So kind of the image would be this blue curve inside the manifold. We can kind of think about the tangent to this curve at the point X. This would be derivative of gamma at the point 0 acting on 1. Note that tangent space to the interval at the point 0 is equal to R, the only one-dimensional Euclidean space. And we are taking 1 as a vector in R. So the tangent space, the derivative of gamma at 0 acting on 1, would be a vector in M in tangent space of M at the point X, this red thing. We could think about any other smooth curve which passes through X at the time 0. Right, there are a lot of other curves inside M, they pass through X at time 0. The tangent space is generated essentially, or is equal, in fact, equal to the derivative of all these curves at time 0 applying on vector 1. So think about all these curves passing through X. If you think about the tangent vector to all of these curves, they all together form the tangent space when kind of translated to the origin. Okay, the final question I wanted to ask. So here we defined the notion of derivative between smooth manifolds. In calculus, we had the second derivative. The question I want to ask, how can one define the notion of second derivative, or can we do that for smooth maps between smooth manifolds? Okay, this is a great place to stop.